Hello, Algebra 2 students. Today we're going to be reviewing for our Unit 11 test covering conic sections. The first lesson that we looked at was just titled Introduction to Conic Sections. This is where we got a basic idea of how things went. Okay, so what we did is we discovered the structure that conic sections are based upon. It's what we call a double-napped cone. And then the conic sections themselves are the result of a two-dimensional plane slicing through this conic section at particular angles and locations, and then opening up the double-napped cone wherever it has been cross-sected and examining the shape of the surface of the cut. And that is what is known as the conic sections. Now, there are four basic conic sections that we had discussed in their basic properties. Some of us did not do a very good job of identifying these when we took a quiz over it, so try to make sure that you know them before the test tomorrow. If you pass a plane through perpendicular to the main axis of the double-napped cone, you are going to get a perfect cross-section of a circle. Obviously, as the plane moves up or down inside of the double-napped cone, it is simply going to generate circles of different radii. Then we discussed what would happen if you pass that plane through not perpendicular to the main axis, okay, particularly just any old angle that happens to actually enter through the lateral face of the cone and exit through the lateral face of the cone as well. What's going to happen is you get one of the axes of the circle is elongated, longer than the other, and you end up with your circle being stretched into what we call an ellipse. And obviously, as the plane tilts further and moves up and down through the double-napped cone, you will end up with one axis being stretched further or one axis being shorter, and those axes growing and shrinking and stuff like that. The third shape that we looked at, what we said was if you passed the plane through the double-napped cone so that it was parallel to an external edge of the cone, you would end up with a parabola. Now, please note it's not entirely imperative that the plane pass through parallel to an external edge of the cone. The point is that the plane will pass through the lateral face on like on this one, as it moves from left to right, it enters through the lateral face, but then it exits through the base of the cone. And when that happens, you don't get the enclosed figure like a circle or like an ellipse, so we end up with a parabola. So it's not absolutely required that the plane be parallel to the external edge. We were just trying to get a little bit of a basic knowledge. Okay, just understand if the plane goes through the lateral face on one side and comes through the base on the other side, you're going to end up with a parabola. The hyperbola is the result of the plane passing through the double-napped cone such that it is parallel to the main axis. Obviously, what we get here is two parabolic intersections with the double-napped cone, but please be aware that hyperbolas are not two parabolas going in opposite directions. Okay, they're a little bit different on their properties, but there are two cross sections and they do resemble parabolas, but not exactly. Okay, now we talked about the equation for the first time, and that's what we spent the bulk of this unit working on, is trying to understand the equation. And if I were you, I would be very, very familiar with the equations of the conic sections. I find it very likely that the vast majority of your questions are going to revolve around identifying the equations or working with the equations or reading the equations, but that seems to be the bulk of the information in this unit is centered around the quadratic equation. Okay, so here's the general quadratic equation: ax squared plus bxy plus cy squared plus dx plus ey plus f. And while it sounds real complicated, it's not that bad. Okay, obviously at the beginning of the equation, we have the x squared and the y squared. After that, we have the x to the first and the y to the first, and then we have a constant. And it's just alphabetical, A, B, C, D, E, and F. Now, I did skip the xy term in there. Okay, we have not used the xy term, and we'll get to it here in just a second. Okay, but it has not been active in any of our equations. But the A, C, D, E, and F have all shown up in various capacities as we have discovered our equations. Okay, the only requirement in order to be a conic section is the A, B, and C terms cannot all be zero. At least one of A, B, and C need to be active in order for this graph to bend. If you allow A, B, and C to all be zero, then you have just graphed a line. Okay, now if your graph does have an A and a C term in it, you are going to have two lines of symmetry. That's something that I added in the notes after we discussed it, but you do need to know this. If A and C are both active in the problem, you will have two lines of symmetry. If only A or C are active, you will only have one line of symmetry. That's important. Okay, we talked about a little bit of a failure in mathematics, or a little bit of a deeper understanding, is the reversal of square and square root. Okay, this goes back all the way to junior high. Whenever you square a number, you always end up with a positive value. Positive times positive is positive. Negative times negative is positive. Okay, so the act of squaring a number steals the sign from that value, and we always end up with a positive term. The result of that is we have no way to get back to knowing whether we started off with a positive term or started off with a negative term. So if we find the need to take a square root of a value, you must consider the possibility that the number coming back out of that square root could have been positive to begin with. It could have been negative to begin with. And when it came time for us to do some graphing the long way, that became very important in order to get our points. Only one other thing to consider here, and I'm going to jump back to the double napped cone here for just a second, if I can find it. Okay, there are some things in conic sections that are referred to as degenerate conic sections. We haven't talked about them really much at all, but I'd like to introduce you to them now, just in case. It's just a little extra tidbit of knowledge here. Okay, a degenerate conic section is the idea that a plane could pass through the double napped cone without actually generating the circle or the ellipse or the parabola or the hyperbola. Such an example would be, what happens if we allowed the plane to pass through and it went right through, okay, the point where the two vertices of the double napped cone join together? What actually would be generated when that happens right there at that location? Okay, well, it's just a single point in the cone, okay, and that's where the plane passes through. Okay, so it is a possibility that your plane could pass through and end up with just a point as the cross section. Since it didn't generate one of the four types of conic sections that we expected, we call it a degenerate conic section. Okay, there's also another one that's out there. Let's say the plane passes through, okay, kind of like it's trying to get the parabola, but let's say the possibility exists that when it passes through, it just catches the edge of the double napped cone all the way across. Okay, so what is this guy going to generate? It's not going to be an ellipse because it didn't actually get into the interior space of the double napped cone. It's not going to be a parabola because, again, it did not get into the interior space, so it can't pick up both lines or both legs of the parabola. So what exactly is it? Well, this is a line. Okay, but so again, it did not generate the type of conic sections that we expect based upon our plane passing through. So once again, we call that a degenerate conic section. So a little piece of vocabulary there for you in case you happen to run into it tomorrow. All right, the next thing we looked at was properties of the conic sections. We're taking a little bit deeper look at the equations on this day. Okay, so back to the quadratic. The day before, the assignment before, we had spent a little bit of time exploring the different equations and looking at what happens with the coefficients for your x squared and y squared. What happens with the signs of your x squared and y squared? Are they both positive? Are they both negative? Is one positive and one negative? Do you have both your a and your c terms active? Are there both? Is it x squared in the problem and y squared in the problem, or is it just one or the other? Those are important things to notice looking at the equation, because that tips us off as far as what type of a conic section we are going to see. And you'd probably be surprised how many questions can possibly be answered just by being able to read the properties of the equation and not even having a graph, just knowing what happens when the coefficients match, what happens when they're different, what happens when the signs match, what happens when they're different, what happens when the degree, the highest power of each variable matches, what happens when they're different. Okay, that's been a lot of what we've been doing here for about the last semester. Okay. Now, we looked at first the parabola. The parabola is the easiest one, I think, to identify because of the dimension mismatch in the equation. If you have one variable that's in the second dimension and one variable that only reaches as high as the first dimension, then the graph is going to bend only one time. That makes it a true quadratic. That makes it a parabola. Okay, circle, I think, is probably one of the easier ones to identify as well. Okay, and that one deals with the situation where you have the x term and the y term both active in the problem, and the coefficients are identical. Okay. Now, as you can see there at the top, there are two different formats for the equations of circles, and we'll get to that more in the next lesson. In fact, I think that's probably the biggest part of the math that you would need to worry about for this upcoming test, is dealing with the equations of the circle. Okay, now down at the bottom, we see the prototypical ellipse. Okay, an ellipse is when you have your both of your variables in the second dimension, yet the coefficients do not match. That's going to cause one of the axes to reach further than the other. That's going to stretch your circle and make it elliptical. Okay, the last one is the hyperbola. And the hyperbola is identical to the ellipse with one critical difference. Okay, you will have your x squared and your y squared terms both active. However, the signs will disagree with each other. You'll have one in the positive and one in the negative, and that's going to make the sides of the graph turn away from each other rather than towards each other. Now, a few minutes ago, we mentioned that we have not allowed the xy term to be active in the problem. Okay, but just remember that what this guy does is xy causes an axis rotation in the graph. Okay, so if the b term should become active for some reason, it does not change what kind of a graph you have, does not change the nature of the graph, it does change the rotational positioning within the graph. So as you can see down there on the left, we have an ellipse where b is equal to 0. And if you allow b to change, well, we still have the exact same ellipse, same center, same major axis length, same minor axis length. However, its axes have been rotated. Okay, now that brought us to a very short discussion about these equations. These are what we call the unit conic sections. I was a little concerned yesterday as we were going through the graphs, trying to identify what equation belonged to those graphs. A lot of people kept bringing these equations up in their notes and going, are these the equations that we use for those graphs? Well, that's a little concerning, because, I mean, if these were the equations to use for those graphs, how do you change the center points and the vertex locations on these graphs? Okay, how do you change your radii and stuff like that? Anyway, these are the basics. These are what we would call the parent conic sections. Okay, but we can't really use the term parent conic sections, because parent really refers to functions, and most of our conic sections are not functions. sections. They fail the vertical line test in most cases. Anyway, so these are what we call the unit conic sections, meaning these are the most basic conic sections that each of the different types of conic sections have to offer. They have not been moved in the graph, meaning they are either centered or vertexed at the origin, and they have not been no crazy stuff has happened to them. We haven't been overly stretched one direction or the other, stuff like that. Okay. That brought us to a more in-depth discussion of the circles. Now, like I said, I find it likely that the hardest math that you're probably going to see is going to lie in the circles. Okay, it's a simple equation, but a fairly difficult conversion can be there if we have to get from one form to the other. Okay, so standard form is the form that we like to see. Okay, that is the x minus h quantity squared plus y minus k quantity squared equals r squared, where of course r represents your radius and hk represents your center. As always, the negative values are built into the formula. They should be there, so if they are not there, that means something about h and k has managed to change them, and that's what we call standard or center radius form. Okay, this one's very easy to work with, very easy to graph from if you happen to have it in standard form. Okay, the only real catch to remember it is, of course, the negatives are built into the formula, and the constant represents r squared, not r. So if you have a 36 like you do up top, you have to take the square root of 36 in order to discover the length of the radius. And at the bottom, that was just to prove the point that the radius does not always have to be a whole number. In fact, many times it will not be. Okay, so you got square root of 29. After all, if you think about the radius does not measure just north, south, east, and west away from the center point. It measures in all directions, infinite directions away from the center point, and that is not very likely to hardly ever put the circle actually on the grid lines inside of the Cartesian coordinate graph. So it really doesn't matter if the radius is a whole number or not, because in most cases when you measure away from the center in a particular direction, you end up somewhere in between the grid lines anyway. So do not let a non-whole number radius surprise you. It is certainly to be expected. Okay, these were very simple examples. All you have to do is read the equations to get the centers and the radius. You can plot the points. Okay. The only thing I said that I expected for you to do for my worksheets was to basically discover your radius and then measure that same distance north, south, east, and west, and then connect the dots. I have no way of knowing what the test is going to expect you to do, or if they're going to have you graphing stuff or simply identifying graphs. I do not know. Okay, but if you do the north, south, east, and west, that should pretty much get you in the good vicinity of the correct graph, and you can go from there. Okay, now the challenge revolved around getting into or from general form into standard form. So if we were in general form, like the equation that we had discussed the previous 2 days, and then we wanted to graph a circle, well, it's basically impossible for you guys at your current ability levels to graph from the general form. It's even challenging for me. Okay, so what you really want to do is you want to be able to get into standard form, and that involves completing the square. Okay, so we ran back through the step-by-step for completing the square, and there they are. If you decide you want to complete the square, okay, that means that your current constant is not working correctly. So we're going to move that constant to the other side of the equation. Then, for whichever variable it is you're looking for, okay, if it's the x's, then look for the first dimensional x, or if it's the y's, look for the first dimensional y. Okay, look at the coefficient of that first dimensional variable. Okay, we're going to complete the square using that value. And to complete the square, we take that number, we half it, we square it. Whatever value that turns out being, we're going to add that value to both sides of the equal sign. This new trinomial that you have built with your variable is going to be able to factor into a binomial squared. Okay. Now, if you have two different variables going on in your problem, meaning you got an x squared and you got a y squared as well, it may be necessary to complete the square for both of those values. Okay, so I worked through an example with you. You see there, the first thing I did was organize the terms. If a problem is given to you in general form, it will probably be done in proper alphabetic and numeric order, meaning the x squareds and the y squareds will be listed first in that order, then the x to the first and the y to the first in that order, then the constant, and it will be set equal to 0 in most cases. So I've organized the problem here by putting all the x values together and putting all the y values together, and then exile the constant to the other side of the equal sign so that we can proceed to complete the square. Okay, now we're just going to take it one variable at a time. Okay, I'd like the x's to turn into a trinomial that can be factored. So just focusing on the x's, I'm going to take the coefficient of the x to the first term, which happens to be a 2 in this case. I'm going to half it, and I'm going to square it. The result of that, in this case, is a 1. I'm going to add 1 to both sides of the equal sign, and then I'm going to install that 1 into the problem where the x's are. So now I have a trinomial that is specifically about the x's. Now I'm going to repeat the exact same process dealing with the y's. Just considering the y values, I'm going to look at the y to the first term. I'm going to take it. In this case, it's a 4. I'm going to half it, and I'm going to square it. And in this case, that gives us a 4 back. That 4 must be added into both sides of the equal sign. So I'm going to install that 4 in a position where it now makes a trinomial with the y values. Now, these two trinomials that we have generated, the one with the x's and the one with the y's, these guys will factor into binomials squared. Okay, so to get to the binomials, okay, we're going to end up with a binomial squared. You have to take the square root of the lead term and the square root of the trail term and keep the sign of the center term. Okay, so in this particular case, that's going to give us an x and a 1 on the x binomial, and the sign between them will be negative. Okay, on the y's, that will give us a y and a 2, and the sign between them will be negative. If you're still struggling with completing the square, I cannot imagine what you are waiting for. Come in and get some help. This is an old skill. You've had several months to digest this. If you still cannot do it, you need to get on the ball before tomorrow's test. Anyway, once you have that, you are pretty much free to graph it. You can read your center, you can read your radius, and you can draw your circle. Okay, the next thing we looked at was equations of ellipses. Okay, so again, we saw the specific formula for ellipses dealing with the center location HK. And we also saw that typically on equations of ellipses, we have a denominator that is involved, and it is the denominators that are specifically responsible for changing one of the axes of the ellipse. Okay, so M and N, which are both the denominators, are informations about the axes. The overall lengths of the major and minor axes, are double the square root of those denominators. So if you take the denominator underneath x and take its square root, that is how far the edge of the ellipse is away from the center in each direction. So we double it, and that gives us the overall length. Okay, same thing underneath y. If you take the square root of the denominator underneath y, then you're going to get the half of the direction, half of the length of the axis in the y direction. Okay, so the negative values are built into the formula as well, and of course, hopefully you know by now, whichever denominator is larger, that is going to cause the ellipse to stretch further in that particular direction, and of course the smaller one would be the minor axis. Okay, so not too difficult to read the equations. You just got to memorize a couple of facts here, but take a look at those if you need to. And some of you are still struggling with how long the axes are. Some of you think it's just the square root. Some of you know it's the double of the square root, but you need to know. Typically, questions do not ever ask us how far is it from the center of the ellipse to the perimeter of the ellipse. They ask for the overall lengths of the major and minor axes. So you absolutely better know that it is double the square root of the denominator. And just as the case is was with the circles, those do not have to be whole numbers. They can end up being decimal points. So that's just the way it is. Okay, graphing them, not too big of a deal. Okay, all you got to do is identify those things. Hopefully we're okay at reading the center point out of the equations. Okay, identifying your major and minor axis is just a matter of identifying the larger of the two denominators and looking at the variable that's in the numerator. And then all you have to do is double the square root of those denominators, and those will give you endpoints. Double the square root gives you endpoints. And then you do the best you can to draw a circular type object. Some of you have been drawing some things that look more like quadrilaterals than they do circular objects. See if you can't do a little better than that on the test. Okay, so ellipses was pretty easy. Equations of parabolas, very easy to identify the equation of a parabola, but there is a risk of some math that they may do to us. They can get us to complete the square on parabolas as well. Okay, so again, we see h and k. The negative signs are built into the formula as they are with all of the conic sections. Either variable can be the first dimensional variable. Either variable can be the second dimensional variable. In fact, that's a very important point because identifying the first dimensional variable as well as its sign tells you the direction of the opening of the parabola. Okay, so gave you a couple of examples working through and identifying them. Some of you struggled a little bit on the quiz identifying the opening direction of the parabola, and that's kind of silly because it's a very simple fact. Some of you just didn't bother to learn that simple fact. Look at your first dimensional variable and read its sign. In this case, the y is the first dimension, and it's negative. Okay, where's the negative y values? Well, they are downward. The second problem there, x is the first dimensional variable, and it is positive. Where are the positive x's? Oh, they're over at the right. No big deal. Okay, what happens if they don't give you standard form for your parabola? And like in the case of this third example here, they did not. It'll be up to us to figure out what that the vertex form is actually going to look like, standard form. Okay, so the key is identify your first dimensional variable. In this case, x is the first dimensional variable because obviously in the problem you have y squared. So I'm going to move x over to the side by itself, and I would like this to start to look like the standard form. Okay, in order for that to happen, it needs to be a binomial squared. In order for that to happen, we need to complete the square of this trinomial. Okay, but the first thing you need to pay attention to always with completing the square is make sure that your lead term, your second dimensional term, its coefficient is a positive 1. If it's not a positive 1, you absolutely must fix that by dividing the entire problem by whatever your coefficient is. In this case, we have a negative 1 in front of the y squared, so I'm going to divide the whole thing by a negative 1, and that flips all of the signs over. Now we have a positive 1 y squared, which is what we wanted. We can proceed to complete the square. So we're going to go to the y to the first term. We are going to take it, we're going to half it, we're going to double it, and that gives us a 9, and that 9 gets added into both sides. By finishing off the binomial, factoring the trinomial on the right side, we're going to end up with y minus 3 squared. And the only other thing to consider is this negative x. Okay, remember what happens when that variable is negative. It not only influences the x, it also influences the h. Okay, so what we actually do is factor that negative away from the entire binomial, in which case you end up with an x and a minus 9 in there, and there's your equation. From there, we ought to be able to identify a vertex and an opening direction, and of course we can graph it from there. And there you go. Okay, which brings us finally to the equations of hyperbolas. Not a whole lot different than reading an equation of an ellipse. However, there's a lot more information to take into consideration for the hyperbola. Okay, so obviously we saw this one. The thing that differentiates this from an ellipse, which on the quiz, some of you did a terrible job. We took a quiz on parabolas and hyperbolas, and some of you managed to graph ellipses through the entire quiz. Not too smart. Anyway, looking at the equation, the difference between this equation and an elliptical equation is that the terms' signs disagree. One of them is positive and one of them is negative. The positive variable in this particular case of the hyperbola tells which direction your hyperbola is going to open. Now, a strange number of you said the hyperbola opens left, or the hyperbola opens right, or it opens up, or it opens down. Last time I checked, hyperbolas go two directions at the same time. So if you said it went just left, then you called it a parabola, not a hyperbola, and that's incorrect. Okay, if you said it just goes down and not up, okay, then that is incorrect. You called it more of a parabola than a hyperbola. So these directions aren't specifically left and right or up and down like a parabola would be. These directions are left and right at the same time. That's horizontal. It opens horizontally. If it's up and down at the same time, then that is vertically. Now the asymptotes, the slopes of the asymptotes can be told by looking at the square root of b over the square root of a. That is always the same, and it does not change when a hyperbola is concerned because this is a property of slope. The numerator of the slope ratio deals always with rise. It's always the y term. And the denominator of the slope ratio is always the run. It's always the x terms. Okay, so asymptotes will always be the square root of the denominator under y over the square root of the denominator under b. Your major and minor axes are still found by the same procedure. Double the square root of the denominators in both cases. Okay, the larger of the denominators will still dictate which axis is major and which axis is minor. And as always, the negative signs are built into the formula. Okay, so I gave you several examples, or a couple of examples there, and as you can probably remember and clearly see on the board right now, there's a lot of information to consider for a hyperbola. Where's the center? Which direction shall it open? Which axis is going to be major and minor, and what are the lengths of those axes? And then the asymptote slopes is kind of like a bonus. It's a double check at the end of the problem. Okay, you can, if you have your major and minor axes correct, then the slopes of your asymptotes ought to agree with where the edges of your box are going to be at. If any one of them disagree with any other one of them, then clearly you are making a mistake somewhere. Okay, so figure out your major axis, figure out your minor axis, plot those points, figure out your slopes, plot those points. If it does not make you a nice, neat little rectangle in your graph, you have done something wrong. Okay, so let's look at a graph real quick. Okay, there's all the information that we need. Hopefully we're getting really good at identifying the center. Some of you are still making some silly mistakes on that. It's time for us to get over that. You've been seeing how to read these centers for about 5 months now. We ought to be able to read them correctly. The direction that the graph opens for a hyperbola always follows the positive variable. Okay, it does not mean that it always follows the first variable that's written down in the problem. Wherever the positive variable is, that's the one it follows. So in this case, that's the x. So our graph's going to open horizontally. Okay, our major axis and our minor axis is going to be the difference between the two denominators and which one is larger. Obviously, the denominator under y is larger, so our major axis is going to follow the y direction, and it's going to have a length of 6 units, double the square root of the denominator. Minor axis is going to be your x-axis, and double the square root of the denominator, 4 units. Okay, plotting those points, we should have a nice little plus sign developing in our graph. Now, if we find the asymptote slopes, that's the square root of the denominator under y over the square root of the denominator under x. So square root of 9 over square root of 4 is 3 over 2. And we have two different asymptotes, one sloping in one direction and one sloping in the other. So from the center point, if we slope up 3 over 2 and down 3 over 2, we end up with points that ought to complete our box. If we've done everything correctly, we ought to be looking at a nice little 3 by 3 perfect rectangle. If you connect the dots, and here's something some of you need to consider. I said this in the notes, I'm going to say it again. Our graph does not enter the box. Some of you are trying to bring your hyperbola all the way to the center point. Center point has absolutely nothing to do with the graph itself. It is simply the center of the graph that is being generated, but it's not part of the graph. Okay. Now connecting the corner points of our box, we end up with our asymptotes. And then if we keep in mind that our graph is opening horizontally, that means we should be to the left of the box and to the right of the box, and we ought to make contact with the end points of the axes or the axis in that direction. So again, notice the hyperbola does not go into the box. It does not go all the way to the center. It stops at the edge of the axis. Okay, there's another one worked out for you in the notes, but I'm not going to spend your time on it now. You can look back and review it if you need to. So that kind of encompasses all of the information that's going towards this Unit 11 test. It seems like a lot of stuff, but keeping in mind that a lot of these things and a lot of these equations read and interpret the same way, and they are graphed the same way. You simply need to learn the little facts about reading the equations, and that means a lot of you are going to have to do the S word that you absolutely hate, and that means study. You are not going to show up tomorrow simply knowing these things unless you spend a little bit of time learning these things. Anyway, that is it. Good luck on the test.